Thank you very much for joining us today. This is the second monthly seminar from OTFS SIG. And today we are very honored to have the inventor of OTFS, Professor Ronny Hadani from Department of Mathematics at University of Texas at Austin, for delivering the talk of today. And our OTFS SIG is based on the SPCC and also the SSC. And you are more than welcome to join us through the mailing list and check out our website. Okay, so today's topic is about Zak OTFS, a waveform for communication and sensing in the delay-Doppler domain, and it is given by Professor Ronny Hadani. I'll have a brief introduction for Professor Ronny. Professor Ronny is an associate professor in the mathematics department of University at Texas at Austin. He also serves as the chief science officer at Cohere Technologies. He holds a PhD in pure mathematics from Tel Aviv University and a master's degree in applied mathematics from the Winterman Institute of Science. And without further ado, please join me to welcome Professor Ronny to give us today's speech. Thank you.
Thank you very much, Lee. So I will move in a moment. I will move to my slides. It's an honor to participate in this meeting. I think the SIG group is. I'm watching the SIG group and I'm following the SIG group, and I think it's a great vehicle for the OTFS community and bringing all the research together. And it's a wonderful initiative. And so just before I start, my Wi-Fi I'm in my home, and my Wi-Fi there is a small chance my Wi-Fi will break down. So no panic, it breaks and then I join again. So if this happens, there's a small chance it will happen. Just wait a minute or two and I will join again, and then we'll continue from where I stop. Okay, so let me share my slides. One second. Okay. So can you see my slide?
Yes, very good. Thank you.
Okay, very good. So, okay, so I'm going to talk about OTFS. The first few slides of my talk will be similar to my old talks. So this will establish some continuity, and they are mainly targeted to people who don't know anything about OTFS. Most of the audience in this group knows quite a lot about OTFS, but still I want to establish some common ground. And after slide 10 or so, I will start to talk about new things, new developments, which I think are of interest to this group of professionals. Okay, so just maybe I can tell you a little bit about the history before I start. So OTFS grew out of more than a decade of research and thinking, and already in 2000, from the beginning, 2015, 2016, I realized there are two versions of OTFS. There is the SFFT version, and then there is the Zak theoretic version. And in the beginning, I thought that they are equivalent. And indeed, under infinite bandwidth and infinite duration, these two versions of OTFS are equivalent. But turns out they are not. Once you introduce filters, once you bound the bandwidth and the duration of your transmission, the two versions are not equivalent. And in fact, I want to argue and try to convince you that the Zak OTFS is the correct version. That's the correct version of OTFS. And the MC and the SFFT version is an approximation. The reason the SFFT version was introduced to begin with was because Cohere was trying to push OTFS into the 5G standard, and back then, and perhaps still now, OFDM was the waveform of choice. So we had to adapt to this reality and come up with a way to implement OTFS over multi-carrier techniques. So this was the motivation to introduce it, although it has merits on its own right, so it's an interesting construction, but there was some business motivation behind the fact that it was introduced first. Just I want to give you a little bit of history here. Okay, so one second, let me see if I can change the slide. Very good. So I will start by talking, the tradition is that every talk starts with few words about the generation which is coming upon us. Now it's 6G. So let me not break the tradition and tell you a few words about 6G to get some broader context. So I will focus on three themes. Channel complexity. People are talking about moving to higher frequencies, beyond millimeter wave to terahertz communication, wider Doppler spreads. So if today we are less than 500 hertz, tomorrow we are talking about 1 to 10 kilohertz. These channels become difficult to model because there are many physical factors, they are difficult to sense, and they are difficult to equalize. The second theme is cloudification of the network. You are moving the control center away from the base station, building big centers of massive computation. In these centers, you want to implement predictive algorithms, machine learning, AI. And here you are, and because of that, you are introducing additional latency, and you have to keep in mind that when you want to predict, you are in wireless, you are predicting environment which is highly non-stationary, and this is a complicated issue because the whole notion of machine learning is when you have some level of stationarity, something can be learned. So in wireless, it's a big question. What are you learning? Okay, and the third theme is joint communication and sensing. It's very gratifying to see that both theories of communication and radar are at last converging, and people are looking for high communication throughput and at the same time sensing the environment in high resolution. So the challenge here is that now you need to be optimal with respect to two goals, not only one goal of high throughput. Now you have to have high resolution sensing. So you are looking for a mathematical framework that facilitates high throughput communication for arbitrary complex channels. You want to predict under dynamic conditions, and you want to conduct joint communication and sensing. And of course, that's a lot to us. But we propose that there is a way forward, of course, and that's OTFS. And OTFS is a paradigm of communication in the delay-Doppler domain, in contrast to the multi-carrier paradigm, which is paradigm of communication in the time-frequency domain. In the OTFS paradigm, you model and process the communication channel in the delay-Doppler domain. This gives rise to the delay-Doppler channel representation. You multiplex the information in the delay-Doppler domain. This gives rise to a waveform or a modulation technique, which is called OTFS. And third, on the most fundamental level, it constitutes a mathematical unification of communication and radar theory, and in this way it establishes a framework for joint communication and radar sensing, because you are doing radar and communication on the same coordinate system, so it lends itself very naturally to do both things. Now I would like to add that today there are, I didn't really count it, I just get from ResearchGate notification. There are more than 1,000 scientific publications about OTFS. I think there are more because what I see is just the citations of the original paper in 2017. So there is a lot of work going on about OTFS, and this is of course gratifying to see. For the sake of this talk, I want to point out two recent publications that I co-authored with Saif, Chokes, and Rob Calderman. And they appear in OTFS Beats on Information Theory. And in these two publications, you will read all the mathematical details of my talk. So in my talk, I will try to focus on pictures and ideas and intuition, because they are very robust intellectual structures. And if you want to fill in the formulas and the details, go to these two papers and you will see all the details there. And they are written in the fashion of magazine papers, so I think they are very readable. So I recommend it. Okay, there is another paper that I'm going to mention in the end related to more recent stuff that I think is interesting for you. Okay, so let me start by saying a few words about the delay-Doppler channel representation. So as you all know, the channel is not some arbitrary structure. It comprises of reflectors. You transmit a wave, it propagates through the environment, bounces off each reflector, and what you get on the receive side is a superposition of all these reflections. Now, every reflector introduces a combination of time delay and Doppler shift, and you can represent this geometry as a two-dimensional impulse response on the delay-Doppler plane. Every tap in this response represents a cluster of reflectors of specific delay and Doppler characteristics. And this is called the delay-Doppler channel representation. And almost by definition, it's the sparsest or the most compact and stable representation of the wireless channel. And its main advantage, of course, it's low dimensional, and it facilitates efficient acquisition, efficient prediction, and efficient equalization. So let me reiterate, because this is very important. The main observation is that the wireless channel is governed by stationary parameters. You have a collection of reflectors. Each has a range, velocity, and some complex gain. Now, the range is parameterized by the delay, the velocity parameterized by the Doppler, and the complex gain factors into multiplication of two numbers, the phase and the propagation loss. And out of these four parameters, only the phase is rapidly changing. In fact, the delay, the Doppler, and the propagation loss are changed very slowly in time, and to a large extent are independent of the carrier frequency, and they form the most stable parameterization of the channel. So you have to take these parameters seriously, and in a sense, every computation that you want to do with respect to the wireless channel should be done or should be conducted with respect to these parameters. Okay, so now let's start the talk, and let's talk about how to multiplex. So if we agree that the delay Doppler coordinates are the correct way to think about the channel, how to multiplex information in the delay Doppler domain, and that's of course the OTFS waveform. So to date, engineers are using three basic waveforms. You have TDMA, which carry information over pulses in time. You have OFDM, which carry information over tones, which are in fact pulses in frequency. And then you have CDMA, which is spread spectrum, which carry information over codes, which are scrambled, which look like noise. So this is looks like a completely different approach. You have waveforms which have no structure; they are completely spread in frequency and in time. So you have these three paradigms or three waveforms, and turns out that these three waveforms are mathematical descendants or degenerate cases or particular cases of a single mother waveform, which is OTFS. Okay, and the OTFS waveform or the OTFS carrier looks like that. It's a pulse train modulated by a tone, or more specifically, it's a sequence of pulses evenly spaced in time, and each pulse is decorated by a phase, and the phases are rotating in the IQ plane. They form a spiral in this complex domain. So they are rotating in the IQ plane according to a specific frequency. So it locally looks like a pulse, it globally looks like a tone, it exhibits properties of both, and we call it a pulson for obvious reason, because it's a combination of a pulse and a tone, okay? And the main characteristic and I'm going to use the word pulson a lot. I think it's important to give something a name, because once it has a name, you can refer to it in a way which is unambiguous, okay? So a pulson, the main characteristic of a pulson is that it remains invariant under the operation of time delay and Doppler shift. And what do I mean by that? I mean that it's not an eigenvector of this operation. What I mean by that is something in a sense reciprocal to being an eigenvector. It's a geometric mode of this operation, meaning that if you translate it in time, it is changing, but it is preserving its shape. And if you shift it in frequency, you are shifting away, but you are getting the same kind of waveform. It preserves its shape. And also, if you take its Fourier transform, it preserves its shape. So it's a kind of a shape invariance. Okay? And this is important because it means that if you transmit a pulson under an arbitrary wireless environment, you have a family of reflections, and each will shift it in time and in frequency, but the waveform preserves its shape. So what you get on the receive side and what you transmitted are very much related to one another. So it's like driving a car with a good suspension system. You can have many bumps in the road, but the suspension just swallow the bumps. You don't feel them. So this is what makes a car, a luxury car. You don't feel the bumps. And this, of course, at least intuitively translates to performance consistency and robustness under various channel conditions. So that's really the intuition. That's really the philosophy or the ideology behind OTFS. And now I will start delving into more technical detail. So it turns out the pulson has a lot of mathematics behind it, a lot of mathematics and physics behind it. And to understand it, you have to go back to the very beginning, and this is the dimensions of time and frequency. Okay, so if you have a signal, you can represent it either as a function of time or as a function of frequency. and these two representations of the signal are related by Fourier transform. Okay? However, time and frequency are not orthogonal dimensions. They do not behave like x and y, the spatial dimensions x and y. And why this is so? Because if you have a signal which is localized in time, when you convert it to frequency, you get something smeared. It is not localized in frequency. And vice versa, if you have a signal which is localized in frequency, when you convert it to time, you get something smeared, so it's not localized in time. So you cannot simultaneously localize both in time and in frequency to any desired degree, because there is a fundamental mathematical obstruction to do it, and this is called the Heisenberg uncertainty principle. Okay, there is no such an obstruction in x and y spatial dimension. You can put your finger any point in the plane. Nature has nothing to say about it. It is allowed. But in time and frequency, it's not allowed. You cannot really pinpoint every point in the time frequency plane because of this uncertainty principle, which makes signal processing very interesting as a side effect. But turns out there is a workaround, an elegant workaround the Heisenberg uncertainty principle. In a sense, the Heisenberg uncertainty principle does not act as a brick wall. It's like a little bit like a rubber band. You can kind of stretch it and twist it. You can play with it. And the way you work around it is as follows. You start with the pulse, and then you extend it to an infinite configuration of pulses in regular intervals. But this is a little bit peculiar. It's not a periodic configuration. It's what is called quasi-periodic, which means that every time you move an interval, you have to rotate by a phase according to a specific rule, which most of you know the rule. But for the sake of this talk, I'm not going to bother you with the mathematical detail of the rule. But remember, you have to apply a certain phase rotation according to some analytic formula. And this is called the quasi-periodic configuration of pulses, or a quasi-periodic extension of the original pulse. And turns out that such a quasi-periodic configuration does not violate any longer the Heisenberg uncertainty principle. The Heisenberg uncertainty principle allows such quasi-periodic pulses to exist. They correspond to real signals, okay? So that's important. Now, as you can see, observe that when you define this quasi-periodic extension, you are free to choose the period, the intervals between the aliases, any way you want, as long as they define a box of area 1, as long as they multiply to 1. And this box is called the delay-Doppler box, or the fundamental domain, or the fundamental period. So in fact, I want to stress that because that's important. The quasi-periodic extension is not uniquely defined. It depends on a parameter, which is the period. In fact, it's one parameter because one period is dictated by the other. So you have one parametric family of such quasi-periodic extensions. Okay? So the next question that you want to answer, of course, is given such a quasi-periodic configuration, what kind of signal in time correspond to it? Okay? To see that, you need to apply a transform, which is called the Zak transform. And when you apply the Zak transform to a quasi-periodic configuration of pulses, what you get is a pulson. Okay? So the pulson is the time realization of a quasi-periodic pulse in delay-Doppler. All right? And this is not really new to you because you've seen something similar before. The tone, the OFDM tone, is the time realization of a pulse in frequency. And the transform, which relates the two in that setup, is the Fourier transform. So in the context of OTFS, you have a delay-Doppler, quasi-periodic pulse in delay-Doppler, and then the Zak transform related to a signal in time, which is the pulson. So you have two different ways to think about the pulson, or about the OTFS carrier. You can think about it concretely as a pulson in time, or you can think about it more abstractly or more conceptually as a quasi-periodic pulse in delay-Doppler. Now, it's interesting and important to understand how the properties of the delay-Doppler pulse map into properties or attributes of the pulson. So, and once you understand that, you have all the physical intuition about OTFS. So the first thing I want you to notice is that the delay period of the quasi-periodic pulse is equal, maps to the gap, to the interval between consecutive pulses in the pulson. So as you can see in the figure, okay? As you make the delay period larger and larger, the gaps between consecutive pulses get bigger and bigger. Okay. Second, the delay coordinate of the pulse translate to time displacement of the pulse train. So if you move the pulse along delay, the pulse train shifts respectively along time. The Doppler coordinate of the delay-Doppler pulse dictates the frequency of the tone. So if you move the pulse along Doppler, the tone oscillates in different frequency. And finally, the width. The pulse has physical width. So the width along delay is inversely proportional to the bandwidth of the pulson, which is exactly the width of the individual pulses in the pulson. And the width of the delay-Doppler pulse along Doppler is inversely proportional to the duration of the pulson. Okay? So as you making the delay-Doppler pulse narrower and narrower in delay-Doppler, what happened to the pulson? It spread over a larger and larger bandwidth and longer duration. So if you want to achieve higher and higher resolution in delay-Doppler, it means that you are using more and more bandwidth and more duration. Okay? And that's the basic, I would say, trade-off in radar theory. You want high resolution, give me more bandwidth, this will give me resolution in range. If you want to a high resolution in Doppler, give me more duration, more sensing time. Okay, so once you understand what is the pulson, once you understand the OTFS carrier, OTFS behaves like any other orthogonal modulation. If you want to transmit a packet, you take the fundamental domain, the fundamental box, you place a grid within it. It's called the information grid. It's a denser grid, and you position a delay-Doppler pulse on each of the grid points. Remember, this is not an individual pulse. Each one of these pulses is a quasi-periodic pulse. Okay, I only show you the fundamental period, and then you modulate a QAM symbol over each one of these pulses, and you transmit this configuration using the Zak transform. Okay, now let me give you a little bit of numerology that you will see the numbers. If you like numbers, this will give you some concrete idea about what's going on here. A typical delay period of LTE kind of system is 50 microseconds. Typical Doppler period is 20 kilohertz. Know the 20 kilohertz times 50 microseconds, if you multiply them, it gives you 1. So this is admissible period. A typical delay resolution, which is the width of the pulse along delay, characteristic width of the pulse along delay, is 100 nanoseconds. And 1 over 100 nanoseconds is 10 megahertz. So that's the bandwidth. Because I told you the width is 1 over the bandwidth. Typical Doppler resolution is 1 kilohertz, and so that's the width along Doppler, and 1 over 1 kilohertz is 1 millisecond. So the duration of the transmission is 1 millisecond. And all in all, if you choose this resolution, you have 10,000 grid points. You have 500 along delay, 20 along Doppler. It's 10,000 grid points within the fundamental box. And notice that 10,000 is exactly 10 megahertz times 1 millisecond. So this is the Nyquist rate. So OTFS obeys all these classical ideas for signal processing. You get the Nyquist rate, you get all these things, albeit in a more, it's kind of a geometric interpretation of the Nyquist rate, because in OTFS, you see the Nyquist rate in a geometric, manifesting itself as a geometric partition of the delay-Doppler box. Usually when you do classical signal processing, the Nyquist rate is some abstract dimension. But in OTFS, it's not an abstract dimension. It's something very concrete. It's the number of grid points in the delay-Doppler box. It's exactly, you have a geometric interpretation of it. Just a curious fact. Okay, so, all right. Now I will start talking about new things, and I will begin with this fundamental curve. This is called the period curve, and you are going to see this curve a lot in my talk. So just, prepare to that. So as I told you, OTFS, the OTFS is not a single waveform. It's in fact a one parametric family of waveforms. And the parameter is the period. And in fact, it's one period dictates the other. Okay, so you can think about the delay period as the parameter. Now, it's convenient to think about the period as a parameter gliding along an hyperbola curve in the delay-Doppler plane. And every point in this curve specify a specific delay-Doppler box with a specific aspect ratio, aka a specific waveform, aka a specific modulation. Okay? And there are three basic regimes to this curve that I want you to consider. There is the regime on the far right, and this is the regime where the delay period is much bigger than the Doppler period, or the Doppler period is very small. So in this regime, the gap between consecutive pulses in the pulson is big. And in the limit, the gap goes to infinity, and the tone structure disappears. And you are left with a single pulse, and that's exactly the TDM carrier, the TDMA carrier. And this is why we call this regime the TDM regime or the single carrier regime. So in this regime, OTFS behaves like single carrier modulation, like TDMA. Okay, the pulson behaves like a TDM waveform. And then you have the other extreme regime on the far left. And in this regime, the Doppler period is big, which means that the delay period is very small. And here, the gap between consecutive pulses is very small. And in the limit, the pulses are just compressed against one another to infinity, and you get, and the pulse structure does disappear in the limit, and you get a continuous tone, which is, of course, the carrier of multi-carrier modulation of FDM. And this is why we call this regime the FDM regime or the multi-carrier regime. And in this regime, the pulson behave like a tone, like a multi-carrier waveform. Okay? And then you have the regime in the middle, where the two periods are of comparable size, they are both big. And in this regime, the pulson exhibits both properties of a pulse in time and properties of a tone. And for reasons that I'm going to explain later, this regime is called the crystalline regime. Okay? And the main driving question of my talk, in a sense, is which regime is optimal for communication and sensing. Okay? Which regime is the correct operating point for both tasks? I'm going to consider both tasks. And I will save you the time, the wait time. The answer to this question is that the crystalline regime is the optimal regime for both communication and sensing, and I will spend the remainder of my talk explaining why. Okay, I'm trying to explain why, and I hope I will convince you. Before I move on, let me just say that I find it curious, in retrospect, it's always in retrospect, of course, that traditionally communication engineers operated in these two extreme regimes, operated either in single carrier or in multi-carrier, not realizing, for evident reasons, that in fact there is a continuous family of waveforms interpolating between these two extreme cases, and the correct operating point is in fact in the middle of the curve and not on the two extremes. So I find it historically curious that that's how things appear, in the history of communication. Okay, so to understand why the crystalline regime is the optimal regime, to understand the answer, you need to understand the answer is encapsulated in the way the channel couples with the pulson in each one of these regimes. And that's what I'm going to explain. So I'm going to go regime by regime and explain the structure of the coupling. Okay? So I will start with the TDM and the FDM regime. So here I'm considering a channel which comprises of 5 reflectors, as you can see in the middle of the slide. So they are represented by points in the delay-Doppler plane. I'm not showing you the complex gain, just the delay-Doppler coordinates. So 3 static reflectors, a house, a building, and a tower, and 2 dynamic reflectors, 2 moving reflectors, which is a car and a bus. And let's say that we are operating in the TDM regime and see what happens. So in the TDM regime, it means that we are sending pulsons with very, very small Doppler period. And if we take, so the Doppler period is so small, so it means that essentially what we are transmitting, just to get a good intuition, we are transmitting a pulse in time. Because the gap between consecutive pulses is so big that it's just single pulse, just ignore it. Okay, the physics will be the same. So what happens when you transmit a pulse in time? This is clear, the intuition about it is clear. This pulse propagates, interacts with each reflector, and what you're going to get on the receive side is configuration of echoes, displaced in time according to the delay characteristics of your reflection. And I want you to focus on the second echo in this picture, because I want you to see that the second echo is in fact a superposition of two reflections which have the same delay but different Doppler. Okay, so the second echo is in fact a superposition of two reflections which alias upon one another. And the word aliasing is very important. I will repeat it again later, so keep this in mind. The two reflections alias upon one another to create the second echo, while all the other echoes are single reflection. But this is a big difference, because what is going to happen is the following. Say you transmit now your pulse not at this point in time, but at a different point in time. So again, what you're going to get at the receive side is configuration of echoes. But now the second echo, because it's a combination of two reflections, the phases are going to add up differently. The way the phases are going to add up depends on the point of transmission, and because of that, they sometimes add up constructively, sometimes they add up destructively, and as a result, this second echo is going to fluctuate both in phase and in, most importantly, not the phase, but in amplitude. Okay, because as you know, when you add up phases, it depends what the phases are, and you get different absolute values. And this is the phenomena of time selectivity. Okay, so this second echo is going to be selective, while all the other echoes are going to be basically invariant, up to phases. Okay, but that's the phenomena of time selectivity. And the same thing happens when you transmit, when you operate in the FDM regime. Now the delay period is very small, which means the Doppler period is very big. So if it is big enough, physically, it means that you are transmitting a pulse in frequency. You are transmitting FDM. That's what it means. Okay, and let's say that you are transmitting a pulse in frequency. What you get on the receive side is configuration of echoes. And here again, you see that the middle echo is a superposition of three reflections, which have the same Doppler, which in this case is 0, and different delays. So it's a superposition of three phases. Okay, and because of that, the amplitude of this middle echo will depend on the point of transmission within the frequency line, and this middle echo is going to fluctuate in phase and in power, and that's the phenomena of frequency selectivity. And again, it originates from the fact that here the reflections are being alias or fold upon one another along the Doppler dimension. So let me just summarize this discussion. The coupling of the doubly spread channel and the pulson in the TDM and FDM regime is selective, namely the response depends on the point of transmission, and it is selective because of this aliasing effect. And I'm going to use these terms, fading and unpredictable, because these are the terms which appear in our two papers that I advertised in the beginning. So I will use the two notions. Okay, so now let's move to the crystalline regime and try to contrast it with what happened in the FDM and TDM regime. So first, let me be a little bit more precise about what does it mean to be in the crystalline regime. So being in the crystalline regime means, well, heuristically at least, that the periods are big. But big is a relative term. Big compared to what? Okay? So the correct thing to say is the periods are big compared to the spreads of the channel. All right? Namely, you assume the delay spread is strictly smaller than the delay period, and the Doppler spread is strictly smaller than the Doppler period. Okay, and here I'm giving you an example. Again, a typical Doppler spread of LTE is 500 Hertz. typical delay spread is 5 microseconds. Okay, so take the delay period to be 50 microseconds and take the Doppler period to be 20 kilohertz. Note that 50 microseconds times 20 kilohertz is equal 1. So these are admissible periods, and these periods are well within the crystalline regime because they are bigger than the spread. All right. So when you operate in the crystalline regime, the two periods are big compared to the spread. So now I'm drawing the delay-Doppler box. I'm not assuming that one of the dimension is 0 because the box now is big in physical sense compared to the spread of the channel. The channel gives you the unit of length in a sense. And let's say that we transmit a pulse within the delay-Doppler box. Okay, a pulse at point P1. All right. And so what are we going to get on the receive side? We are going to get a response, which I will denote by R1. And the structure of the response, this is a configuration of echoes, which displays in delay-Doppler according to the delay-Doppler characteristics of the reflection. Okay, it's a two-dimensional response. And because of the crystallization condition, namely that the period is bigger than the spread, this response is confined within a single period. That's important. The whole response is confined within a single period of the pulson, of the delay-Doppler pulse. So let's remember that. And now let's say that we transmit a pulse at a different point, at the point P2. Okay? So what are we going to get? We are going to get a different response, let's say R2. Now, here is the main statement. When the crystallization condition holds, turns out that these two responses are equal to one another. Okay? So what does it mean? It means that when you operate in the crystalline regime, the response that you get is independent of the point of transmission within the delay-Doppler plane, within the delay-Doppler box. So there is no selectivity. And this is in sharp contrast to what happened in the TDM FDM regime, that you saw that the response is changing all the time as you move along the domain. Okay? So in the crystalline regime, the response stays the same. So there is no selectivity. In particular, there is no fading. So there is this invariance. You get the same response at every point. And this is why it is called the crystalline regime, because this is a structure of a crystal is a pattern which repeats itself again and again and again and again. It's repetitive. And that's exactly what happened here. That's exactly the coupling in the crystalline regime. The coupling is a crystal. Okay? Now, there is a small caveat here, and I want to point it out. This equality is not precise equality. It's something a little bit more subtle. This equality means that the two responses are related by a function, namely R2 is a function of R1, and this function depends only on the vectorial distance between these 2 points. And specifically, it says this function is as follows: the amplitude of the individual echoes is the same, while the phases are different, and the phases are related by a functional relation, which depends only on the vectorial difference between the 2 points. Okay? But to every practical purpose, this is equality. You can work with it as if it is equality. You can devise algorithms that use it. No difference. Okay? So I will relate to it as an equality, although it's not equality, it's a functional relation. Okay? So this is why we call it predictability. It means that response R2 can be computed out of response R1 using an analytic formula which is predetermined. You don't need to learn it. It's an analytic formula. Okay, so let me summarize the discussion. In the crystalline regime, the coupling of the doubly spread channel with the OTFS waveform becomes a crystal, in the sense that it's now the response is invariant, is independent of the point of transmission, and we say it becomes predictable and non-fading. Okay? Good. So let me try to give you an intuition why that's the case. Why, when the crystallization condition holds, things crystallize. So let's say that we transmit a pulse in delay-Doppler, And let's assume that the crystallization condition doesn't hold. Namely, let's assume that the Doppler spread is bigger than the Doppler period. Okay, so what is wrong? What is so wrong about that? All right, so to understand that, you have to remember that what you actually transmit is not a single pulse, but a quasi-periodic configuration of pulses. Okay, and what you actually receive is not a single response, but a configuration of responses. And these responses, because the Doppler spread is bigger than the period, these responses are self-interacting and interacting with one another. And in these regions of self-interaction, phases are being added up. You have aliasing, phases are being added up. And because phases are being added up, this will create a selectivity. So fading and unpredictability will occur in these regions of self-interaction. So once you have self-interaction, the response will start changing as you move around the box. Okay, because you have these phases which add together. And you should contrast it with what happened in the crystalline regime. Now all the responses are disjoint from one another. Nothing interacts with nothing. Phases are not being added up, and as a result, you get this invariant or this predictability phenomena. So this picture, I think, of self-interaction on the left and disjointness on the right gives you the intuition why you want the crystallization condition to hold. Why you want to choose the periods to be bigger than the spreads. Okay, before I move on, I still want to dwell on this point because I think this point is very revealing. I want to take this understanding, this new understanding of where selectivity comes from, and apply it to the classical notion of time and frequency selectivity. So people know about time and frequency selectivity, but I want to argue that until recently, we didn't really understand what are we talking about. And now when we have this delay-Doppler perspective about signal processing, we understand the mechanism behind selectivity, the deep mechanism behind selectivity. So let's talk first about time selectivity. Time selectivity is associated with TDM, or more precisely, it means that we operate in the TDM regime. Okay, so what does it mean that we operate in the TDM regime? It means that the Doppler period is very small. The pulson admits Doppler period, which is very, very small, which in turn means that any small amount of Doppler spread will create aliasing along Doppler. Okay? And as a result, this aliasing will cause selectivity along delay, which is time selectivity. So when your Doppler period is very small, which is the TDM situation, every small amount of Doppler will create aliasing along Doppler, which in turn will create selectivity along delay. So time selectivity originates from aliasing along Doppler. Okay? Aliasing of the responses. And reciprocally, frequency selectivity is associated with operating in the FDM regime. And here it means that the delay period of your pulson is very, very small, which in turn means that if you have a small amount of delay spread, it already creates aliasing along delay or self-interaction along delay. And as a result, this will cause selectivity along Doppler. Okay? So selectivity or frequency selectivity arises from aliasing along delay. All right, so the mechanism behind selectivity is aliasing in this quasi-periodic world of delay Doppler signals. The action of the channel on the pulse becomes alias, the alia unfold on itself. It's kind of self-interaction. And this, I think, is a new insight about selectivity, which is very important, because once you understand that this is the mechanism behind selectivity, you understand how to combat it. You combat it by creating large enough period, and in this way avoid this self-interaction. So now I'm going back to my period curve. I told you that you will see this curve several times in my talk. And now I argue that we understand at least part of the answer why the crystalline regime is the optimal regime. And this is because in the crystalline regime, the channel coupling crystallizes, namely it becomes non-selective or predictable and non-fading. Now, intuitively, I hope that you understand that this is an important thing to have because it has many implications on your system architecture. But I'm going to focus on this talk on two fundamental benefits. And one benefit is that it immediately implies superior uncoded bit error rate performance under perfect channel state information. That's a very theoretical result. You get better bit error rate performance under perfect CSI uncoded. And the second benefit is superior bit error rate performance under non-perfect CSI. And here I'm going to focus on a specific mode of operation that is probably familiar to you, but I'm going to make it precise, which is called model-free mode of operation. So this is the mode of operation that I'm going to consider and show superior bit error rate performance in the crystalline regime. So let me start this performance evaluation discussion. So let's start with the perfect CSI. So I'm going to consider the vehicular channel model. So specifically, the delay spread is going to be 2.5 microseconds, and the Doppler spread is around 800 hertz. 800 hertz corresponds roughly to 250 kilometers per hour at 3.5 gigahertz. And I'm choosing 3 representative points along the period curve. So now I have a channel, so I'm choosing a representative point with respect to this channel. 1 point represents the TDM regime with Doppler period of 500 hertz. Another representative of the FDM regime with Doppler period of 1 megahertz, which is 1 microsecond delay period. And notice that 1 microsecond is smaller than the delay spread. So it is outside the crystalline regime now with respect to delay spread. And the first was in the TDM regime because the Doppler period is smaller than the Doppler spread. Okay, and the third point, I take Doppler period to be 15 kilohertz, which is well within the crystalline regime with respect to this channel ensemble. Okay, and these are the uncoded bit error rate performance graphs. I decorated them for you because this is taken from a paper, so you have somehow it's a bit overloaded. But what you can see from this graph is that the uncoded bit error rate performance of the pulson in the crystalline regime is superior to that of a pulson on the FDM and the TDM regime. And the reason for that is well understood because the dominant error event in uncoded performance is fading, as you all know. And if there is no fading, if selectivity is eliminated, this error event just is being eliminated, and as a result, you get superior uncoded performance. Okay? So that's a fundamental benefit of the crystalline regime. Okay? What happened when you add code? Well, that's a different discussion, but it should be discussed. But uncoded performance is from fundamental reasons better. Next, let me move on and discuss performance advantage under non-perfect channel state information. And as I told you here, I'm going to focus about a model-free mode of transmission. And what do I mean by that? The transmit packet comprises of 2 regions. One is a pilot region, consists of a single pulse, and the other is the data region, comprises of multiple pulses modulated by QAM symbols. So this packet structure is being transmitted using the Zak transform, interacts with the channel, demodulated with the inverse Zak transform, sampled again on the information grid. And what you get is the following. In the pilot region, you get some sampled response of the channel. Okay, some sampled response. And in the data region, you get some convoluted superposition of responses, which is again the action, the coupling of the channel with the data. And model-free mode of operation means that you take the sampled response from the pilot region. That's the only information that you have about the channel, and I want to stress that the only information that you have about the channel is the observation that you make in the pilot region. And by means of observation means I'm measuring the sampled response. I'm not assuming the number of reflectors. I'm not assuming that even there are reflectors. Maybe it's an accelerated system and this response represents acceleration or other physical phenomena. I don't care. I just take the sample response. I'm not assuming anything beyond it. I take my measurement and I'm using it to equalize the data. Okay, and the question is, what kind of uncoded performance do I get in each regime? Okay, so I hope I'm clear about that. I take a sampled response and I'm not adding any additional knowledge to it. All right, and I'm using it to equalize my data, and the results are as follows. So as you can see, the best curve is the star curve, and this represents the perfect CSI performance. Perfect CSI means it's unrealistic mode of operation. It means that I know that the interaction of the channel. I have an oracle that tells me how the channel interacts at every point of my packet. Okay? It's not realistic, but it's a benchmark. And then you see the TDM, the FDM, I decorated it, and the crystalline, and then you can see TDM and FDM just break down completely. This is too much Doppler, so too much delay, too much Doppler. I think it's the same channel as before, 800 Hertz, 2.5 microseconds. So in TDM and FDM, if you use a single pilot, it completely breaks down because whatever you measure at the pilot is not relevant anymore for the data because of selectivity. So the measurement that you did in one point is irrelevant at another point. And in the crystalline regime, you measure it at one point and you can apply it in any other point, and it gives you almost the performance of perfect CSI. Okay? Very good. So that's something fundamental. Now, you can try to dance around this problem. For example, in TDM and FDM, you can put multiple pilots. You can try to interpolate between the pilots, and that's what people are doing. But that's not model free. This means that you start to assume some assumptions on your channel. You're applying some additional signal processing. I told you, take the sampled response, take only the observation that you have, don't do any additional signal processing, and use it to equalize. Okay. This is important, so I want to slice this result from a different angle. So again, model-free mode of transmission, okay? But now I want to show you the performance, not as a function of SNR on the x-axis, but now I'm fixing the SNR to be 16 dB, and I'm looking at the performance as a function of the Doppler spread, and I'm changing the Doppler spread from 500 Hertz to 4 kilohertz. That's what you see on the x-axis. And here I want you to see. So the two red curves are TDM and FDM, break down completely. Don't give you performance. That's just no performance at all. 500 Hertz is already a lot of Doppler for TDM, and just as you increase the Doppler, it doesn't work. So you need to do some fancy stuff, but roughly it doesn't work. Zak OTFS, it's the blue curve, and you see it maintains flat performance. It just performs uncoded beta rate of 10-2 at all Doppler. Doesn't care about the Doppler at all, exactly because of this crystallization phenomenon. As long as the Doppler is smaller than the period, fine. Zak OTFS is not selective. You measure at one point, you apply it at another point, no problem about that. But in this graph, I included another interesting curve that I want you to see, and that's the black one. The black one is interesting because the black one is the performance of MC-OTFS, of the SFFT-based OTFS, which is recorded over OFDM or over multi-carrier. And as you can see, MC-OTFS, up to 1 kilohertz, perform the same as Zak OTFS. Beyond 1 kilohertz, it starts to degrade quite quickly. And that's because MC-OTFS is not predictable, does not crystallize in the sense that Zak OTFS does. Namely, if you know the response in MC-OTFS for large Doppler, beyond 1 kilohertz in this case, if you know the response of MC-OTFS at one point, you cannot deduce from it the response at other points. That's the fundamental difference between Zak OTFS and MC-OTFS. Zak OTFS, for mathematical reasons, does crystallize, while MC-OTFS does not. And if you want to understand in more mathematical details what's going on in MC-OTFS and what is the exact difference in the input-output relation, go to the second paper that I recommended in the beginning with Chokes and Saif and Rob, and there is a page discussion about the difference between this, you know, it's a fine difference. Again, I have to admit, I didn't realize this difference until late in the development of OTFS. I realized that Zak OTFS and MC-OTFS are different only around 2017, while the two versions existed since 2013 or 14. So I thought they are the same, but they are not. And I think it's important to understand the difference, whatever it is. Okay, so now let me move to radar sensing, and then I'm going to combine communication and radar and talk about JSON. Okay, so radar is a simple problem compared to communication. Communication is a complicated problem. Radar is simple. In radar, you are transmitting a signal into the environment. You are sending your battle into the sea. The signal interacts with the environment, probes the environment. Radar engineers like to say probe the environment, and you get a response, and from the response you want to read the parameters of the environment. It's a parameter estimation problem. Okay, and I hope that by now at least it's intuitively clear that whatever signal you send, it's a pulson. So either you can use single carrier, which means that you are sending a pulson in the TDM regime, or you can use multi-carrier to do radar, which means you are sending a pulson in the FDM regime, or you can send a pulson in the middle of the curve in the crystalline regime. So now we have a unified framework. Everything is a pulson. I like to think about the world as just different kinds of pulsons, because then I can compare one modulation to the other. Yeah. So in which regime you want your probe to be? Okay. And the answer turns out to be the crystalline regime. Because when the pulson is in the crystalline regime, remember what you receive is not a single response, but multiple responses. And when you do radar sensing in the crystalline regime, the responses are disjoint. And because they are disjoint, there is no ambiguity, and you can read the channel parameters from a single response, from the response in the fundamental box. So you can read, there is no ambiguity. Things do not interface, do not fold on one another and create ambiguity, and you can read the parameters of the channel from the fundamental response, and then apply all kinds of parameter estimation techniques to get precise values, but that's a different topic. But at least you don't have this ambiguity which is created by folding. Okay, so clearly the crystalline regime is the correct regime to do radar. And now let me combine the two systems, the communication and the sensing system, to one architecture. But before I do that, I owe you a debt. Okay, I want to return a debt from the beginning of my talk. Because in the beginning of my talk, I told you that OTFS generalizes the three waveforms: TDMA, OFDM, and also CDMA. But so far, I only explained why OTFS generalizes TDMA and OFDM, because I explained that TDMA is just a pulsons with delay period, with big delay period which is much bigger than Doppler period. And I explained that OFDM, namely tone, is just pulsons with very big Doppler period, or Doppler period which is much bigger than the delay period. And then you have, and then the bottom edge of this triangle is just all the other families of the pulson. You can interpolate along the curve, different aspect ratio, different pulson. In particular, in the middle, you have the crystalline regime. But we explain, in a sense, the bottom edge of this triangle. But I still owe you an explanation of how to account to CDMA in the framework of pulson, in the framework of OTFS. So how do you extend the framework? And turns out there is a very elegant way to do that, to account for CDMA phenomena, to create CDMA-like waveforms. And the way you do that is by introducing misalignment, between the generators of the period grid and the delay-Doppler axis. Okay? So far, in the bottom edge, no matter where you are located in the bottom edge, you are changing the aspect ratio of the period grid, but the period generator are still aligned with the delay-Doppler axis. If you want to interpolate in the direction of CDMA, you need to create misalignment between the generators of the period grid and the delay-Doppler axis. For example, rotate the axis of your period grid. Okay, so now once you rotate them, they are misaligned with the delay-Doppler axis. So now you are considering quasi-periodic pulses with respect to a rotated period grid. All right, and turns out that when you look at the power profile in time or in frequency, by the way, of such rotated pulsons, it looks like noise. It's in fact, it's spread, it's smeared. Okay, in fact, it's better than noise. It has constant modulo, very low PIPR. Okay, but it's not like the traditional pulson that is spikes this pulse train. It's not a pulse train anymore. It's something which is completely flat. Okay. Now, if you want to, maybe before I explain that, if you want to read more about this rotated pulson, I want to point you to the third paper that it's not published yet, but it is posted on archive, again with Saif, with Chokes, and with Rob. Zak OTFS for integrating sensing and communication. Most of this paper is devoted to explaining these generalized pulsons. Okay, and let me just mention here that the vehicle to interpolate along the circumference of this triangle, if you want to move from FDM to TDM to CDM, you do it by the vehicle to do it is a certain family of discrete delay-Doppler filters, and all the details are contained in this paper. Okay, and in fact, we are planning to publish a more elaborate paper that will follow this paper, which explain even a more general framework for that. But I want to stress that the notion of a pulson can be generalized in a very geometric way to account also for noise-like waveforms, while keeping all the good properties of the pulson. These rotated pulsons behave exactly like pulsons in all respects. You have crystallization, you have, non-selectivity, all the properties that you have for standard pulsons, you have these rotated pulsons, but they do not look like pulse trains anymore. They look like kind of, they have a shear properties, they have all kinds of properties. They are interesting structures to study. Okay, the two main benefits of these rotated pulsons are twofold. One, they have low PIPR. In fact, they have constant modulo. So not like pulse train. So they have low PIPR, which is very important for radar and also for communication. And second, they are strongly unbiased with respect to standard pulson. So if you consider a standard pulson and you consider a rotated pulson and you look at their inner product, the inner product is very small. It's 1 over square root of n, n is the dimension, n times m. Okay, so they are strongly unbiased. They are strongly unbiased also after they both go through a channel. So it's like one behave like noise with respect to another, low interference. Okay, so this is important to know. Because using these rotated pulsons, now I want to propose an architecture for joint communication and sensing. So the way this architecture works is as follows. It comprises of two signals. One signal will carry communication and the other signal will carry sensing, and they will be superimposed on one another. I'm not going to share resources, so it's not going to be wasteful. So the communication signal is comprises of information bits which are modulated over standard pulson, just OTFS, standard OTFS. Okay, standard pulson, and you modulate information bits on top of it. And the sensing signal is going to comprise a rotated pulson. Okay, one rotated pulson which will act as a probe, and these two signals are superimposed on one another and go through the channel. Now, because the two pulsons, the rotated and the standard, are unbiased with respect to one another, you can think about the output of the channel as the sensing signal corrupted by a low interference from the communication signal. Okay, it all depends, of course, on the power allocation between sensing and communication, but because they behave like nodes with respect to one another, you have a lot of processing gain. So you can think about the output of the channel as the sensing signal corrupted by some interference, low interference from the communication, and you can just reject this interference, push it into the radar sensing module, and get the radar image of your environment, which is basically, okay, parameter estimation, but in particular also channel sensing. Okay, and then you can use this radar image and combine it with the crystalline pulson to subtract the interference of the sensing signal from the output of the channel. And as the output of this interference subtraction module, you will get a clean communication signal, quote unquote, relatively clean communication signal, which you can push into the data detection and retrieve the information. Okay? So here I'm using standard pulson in the crystalline regime to do communication, and I get all the benefits of crystalline regime for communication system while using rotated pulson in the crystalline regime. The period of the rotated pulson will still be bigger than the spread. So I will use sensing pulson, rotated sensing pulson in the crystalline regime to do sensing, superimposed on one another, and in this way I can achieve a close to optimality with respect to both tasks. In fact, you can include another turbo cycle into this diagram, and in this way really match the performance of a system that as if the two systems are decoupled from one another. So that's the architecture that we propose. And let me show you briefly some performance graphs. So again, I have two architectures. One is the superimposed architecture, and I'm going to contrast it with what we call shared architecture, where you share the resources of sensing and communication. So shared architecture means that I'm doing both the communication and the sensing using standard pulsons, the same pulson for both tasks, which, okay, in plain language means that I'm taking my frame, my packet, and I'm splitting it into a pilot region or sensing region and data region. Okay, that's what you do. And I'm going to consider two cases. One is when the pilot region is big, which means it's a whole strip along Doppler, and one when it is small. I don't want to waste too much resources elements. And let's compare the performance. So I'm measuring the throughput for different Doppler spread. And I'm measuring the throughput, you know, the effective throughput. It means 1 minus the bit error rate at 16 dB times the QAM, the QAM capacity, times the QAM order. Okay, so as you can see, the superimposed give you superior effective throughput, the shared give you inferior, and just I want to note, the pink shared is the one with the full strip. It gives you flat performance for all Doppler spread because you devoted a lot of resources to the pilot, but there is some fall in throughput because you are sacrificing a lot of degrees of freedom for channel sensing. So you are just paying a price from the beginning. You are paying a big price in throughput just for the fact that you are allocating a full strip, a full strip as a guard band to do sensing. And then the other setting where the pilot region, the guard band is small, you see that for small Doppler spread, the performance of the shared architecture almost match the superimposed architecture, but it degrades very quickly because as you increase the Doppler, the guard band is not enough. So the channel just leak out of the guard band, contaminate the data, and this contamination is high power contamination because you are using the same pulson, so there is no processing gain anymore, and this just very quickly degrade your performance, or your system breakdown, which is a very bad thing to have. So when you work with superimposed, when you work with these unbiased pulsons, rotated and standard, there is no waterfall. It's a graceful degradation because it's an SNR type of degradation, power degradation. But while we use the same pulson for both stuff, it's like once you have contamination, boom, you get a waterfall, which is a very bad thing to have in a system design. So done. So I'm almost at the end of my talk. That's it, last slide. So let me summarize the key takeaways for my presentation. OTFS is a universal family of waveforms that admit TDM and FDM as limits. So as you can see on the right, you have the period curve, three basic regions. You have the TDM region on the right, the FDM region on the left, and the crystalline region in the middle, where the periods are strictly bigger than the spread. And the crystalline regime is optimal. So the crystalline regime is optimal for communication because the coupling crystallizes, become non-selective, and this yields superior performance under perfect channel state information and superior performance under non-perfect channel state information, namely model 3. Within the crystalline regime, OTFS is optimal for radar sensing because you can read the parameters of the channel from a single response. The responses do not alias on one another and you have no ambiguity. Within the crystalline regime, OTFS is optimal for joint communication and sensing because using this pair of unbiased pulsons, you can design architectures which don't sacrifice capacity and they are very robust and enjoy the good properties of pulson both for communication and for sensing without sacrificing one another. Another byproduct of this discussion of rotated pulson is the OTFS is a generalized spread spectrum, it's generalized CDMA. At least the scrambling aspect of CDMA, because spread spectrum you really want to talk about bandwidth expansion, but that's a different phenomena that you can deal with using a different notion in the OTFS. But the scrambling, the coding aspect of CDMA, you can account for it by in a geometric way. You can account to it by rotating the period grid, and in this way you get CDMA which have the capacity of OTFS. It's like CDMA of steroid. It brings back the whole CDMA advocates into the game because now you can do CDMA without paying the price. You are doing OTFS, which looks like CDMA. It's like being with and feeling without. Okay? And because a priori CDMA was not a good modulation because it did not achieve capacity. The coupling with the channel was horrible. You had to use rate receiver, global interaction. You cannot really achieve capacity. It's very difficult. But in this Zak theoretic CDMA, clear. And finally, just the two basic advantages of OTFS that is always nice to mention. It requires no cyclic prefix because it embraces intersymbol interference. The interferences are being equalized. So that's it. You just acquire the intersymbol interference, fully acquire it, at least in Zak OTFS, not in MC OTFS, and then equalize it. So you don't need to use all these peculiar mechanisms which reject interference. That's the whole idea of OFDM, is to include additional artificial mechanisms to reject interference so that you will be able to equalize. But all these mechanisms are fixes for a problem that eventually shows its head and cannot be fixed. But in OTFS, you embrace the ISI and you just equalize it. Okay? And the other advantage is there is no intercarrier interference. Again, you don't need to use cyclic prefix because you're not rejecting anything, and no intercarrier interference because, again, for the same reason, you acquire the interference in a precise manner and you just equalize it, and that's it. In fact, it's a source of diversity. And finally, that's the last slide. Beside the thank you, I want, again, for this team, for this group, the third book about OTFS. I think there are two books already published, one by Viterbo and the other one, I forgot the author, but it was the first book was in fact published 2 years ago in River publication. So now a third book is about to be published, I think in 1st of September. And again, I want to advertise this book just a little bit. There are 2 big chapters in this book, which elaborate on the 2 papers that I mentioned in the beginning. So if you're a student and you want to read with all the proofs and all the details and all the calculations, you should consult these 2 chapters. And again, they were written, Saif sat down and calculated every point and everything and made all the proofs, So it is written in a language which I think is very accessible to the engineering audience. And just a small remark about the cover picture. If you don't read about it, I like very much the cover picture. What you see is a solid landscape, which have a crystalline formation, and that represents the delay-Doppler domain with its crystalline attribute of the input-output relation, and the landscape interface with an ocean, which is a liquid landscape, which is a liquid medium, which represents the wavy attribute of the pulson. So you have the duality of the wave of the pulson with the crystal of the delay-Doppler input-output relation. So that's what this cover picture is. Okay, thank you very much, and I will stop here.
Thank you, Ronny, for the great presentation. And it's really good to see the book is coming out soon. And I really like the cover, by the way. It's very nice. Okay. We have collected several questions, and I hope you have time to answer some of them. Okay. And the first question, the first question is about the channel parts. And people are asking, is it possible, I mean, or is it reasonable to assume that the delay and Doppler is always unchanged within the transmission? In the sense, is it
again, with the delay Doppler unchanged doesn't matter. That's the point that I was trying to make. I don't care. Okay. That's a very important point, because people have the thinking that OTFS only works when you have a reflector interpretation of the channel, namely the delay and Doppler are fixed. But that's not true. And I tried to say it several times. I don't care what the channel is. I don't care what is the physical mechanism of the channel. Now, I will say it, I will not explain why, but I'm going to say it. And I'm standing behind it. I don't care what is the physical mechanism of the channel. For all I care, the channel can be a very complicated kind of physical mechanism, not reflectors, nothing. Okay, changing Dopplers, changing delays, accelerations of I don't care. As long as the delay Doppler representation of this channel, the effective spread of this delay Doppler representation is smaller than the period, I have crystallization.
I see.
So it doesn't. So that's the strength of the model-free approach. You see, because model-dependent approach assumes that you know something about the physics of the channel, and you use it in order to facilitate channel estimation. And then you are going into complicated bands, complicated situations. So the model-free approach doesn't assume anything about the channel. You take the sampled response, you don't care about what is the physical interpretation of the sampled response, and you equalize it, and you will get the guaranteed performance. Yes.
I also have a personal follow-up question on that. You have mentioned that the actual channel behavior does not really matter in this game, but I'm curious, in the sense of a fractional delay or Doppler, it's hard to say that we have a maximum delay or a maximum Doppler. Well, that case, in this case.
Okay, so now you're asking a good question. When I say channel, I'm saying the sampled response.
Okay. Yes.
So I'm not really saying the physical channel. So what is the sampled response? Let me be precise about that. It's the physical channel. Twisted convolve. Okay, I will use the terminology of Zak OTFS. Is the physical channel with the transmit and receive filters, which conjugate it. So it twisted convolve with the transmit and receive filters. So this is what we call the effective channel, sampled on the information grid. So you have the physical channel. The physical channel can have fractional, whatever you want. You convolve it, or you twisted convolve it with the filter. Okay, you cover it with the filter. You get the filters. You know, they extend a little bit the spread of the channel. You get the effective spread, and then you sample the filter channel on the information grid, and that's the sampled response. In Zak OTFS, the sampling of the effective channel is enough to equalize the data in a non-selective way. So all these fractional, non-fractional, they are not relevant. Okay. So whatever the sampled filter channel is, that's what you use.
Right.
Now, yes, I hope I'm clear.
I think I understood what you mean.
Think about TDMA. Think about TDMA. Forget about OTFS. In TDMA, the channel response is the convolution, not twisted convolution, of the physical channel. Let's assume LTI. The physical the LTI channel with the pulse, with the shaping pulse. So if you have fractional delay, you'll get you will experience, and then you sample this. You take the delay response of your channel, you convolve it with the shaping pulse, and then you sampled on the grid. And if you have integer delay, you will have very nice. But if you have fractional delay, you will experience the lobes of the filter, of the shaping filter. So what you really care is about the structure of the sampling of the filter channel, of the channel convolved with the filter. And whatever it is, this is what will affect your data. The same thing happens in OTFS. The channel now is a two-dimensional delay-Doppler response. The filter now is a two-dimensional pulse in delay-Doppler. The action of the filter of the channel is given by twisted convolution, not by linear convolution. And you sample the filter channel on the information grid, and that's what is related to, that's what you need to equalize.
That's right. That's right. I fully understood. And that's actually leads to another question from me, that because the channel you see is after filtering, that means if the filter, for example, in the delay-Doppler domain is not narrow enough, you will still have aliasing that maybe it turns going out of this so-called fundamental rectangle. Is that give you any penalties?
No. Again, it's hard to, you need, I know it's hard to reconcile between what I say and your intuition, but the intuition is wrong. For a fixed frame, for a fixed frame, within a fixed frame, the action of the channel globally on all the frame, fixed frame has a specific duration, a specific bandwidth. For a fixed frame, the channel have a fixed delay-Doppler response.
Right.
This delay-Doppler response takes into account all the time-varying aspects of the channel within the frame. You only, in this delay-Doppler response is one for the whole frame. And of course, you look at the effective response once you convolve it with the filter, and the spread of this effective response. This is what needs to be smaller than the period.
Yes.
Okay.
I agree.
Of course, you can argue, well, this effective response might be big because of all kinds of acceleration. Not much. Accelerations are not too big. So it's not too difficult to adjust your period to be big enough with respect to the effective response of the channel.
Yes. Thank you for the answer. Yes. Okay. Still, questions about the channels. People are asking if there are any other benefits of OTFS, in particular to the non-doubly selective channels, for example, quasi-static channels. I would assume it's still good.
I think there were people, again, the idea of OTFS is the following. There is no selectivity.
That's right.
So let's take, for example, LTI channel without Doppler. So for channel without Doppler, OTFS in the crystalline regime will be non-selective. But if you think about LTI channel, the crystalline regime, it is bounded from above, but it is unbounded from below. You can take your Doppler period to be as small as you want, and you will still be crystalline because there is no Doppler in the channel. So in fact, for LTI channel, all the OTFS variants, starting from specific Doppler period and lower, will be non-selective, in particular TDM. So again, I want to advertise the idea that both TDM and FDM are just variants of OTFS in these extreme regimes. So for LTI channel, for example, TDM is as good as any in the crystalline regime. TDM is still in the crystalline regime for LTI channel. You want to be in the crystalline regime. So for certain channels, TDM is still in the crystalline regime.
Yes. Yes, I agree. Okay. So how much pilot power do we normally use to have a really relatively good channel estimation accuracy?
Great question. Great question. So we experiment with it quite a lot. You will see the details in the third paper that I said. We find out that when you are using, at least that when you are using the superimposed architecture, we are using comparable energy. So the pilot energy have energy which is comparable to the whole data energy. So take all your data, sum the energy of all your data, not a single data point, and the energy of the pilot is more or less is comparable in size. It can be 5 dB bigger, but it's comparable. It's not so a very energetic pilot, and you are not sacrificing PAPR. Think about it. When you use standard pulson with very energetic pilot, because you want to get a very precise sensing, you will get huge peaks. The PAPR is unbearable, but when you use spread pilots, the spread pulson smeared, and you are not saying you can really use powerful sensing probes And we, from our experiments, you want the energy of the sensing system to be comparable to the energy of the communication system.
Mm-hmm. Thank you. There are also a question regarding your slides, page 26, where you compare the performance of OTFS and the TDM FDM. People are wondering, so the pilot, what kind of pilots are used for TDM?
I use the simplest. Okay, so I use the model free thing.
Yes.
You're talking about the model free or the perfect CSI?
I think
perfect CSI there is no pilot. Perfect CSI you just know the input output.
For sure. I guess it's the model free.
So okay, so I want to be more precise about model free. I consider, for the sake of the explanation, the simplest pilot structure. So I'm devoting a strip for the pilot, a full strip, a full Doppler strip for the pilot in the delay Doppler domain. So in a sense, I'm doing shared sensing and communication. But in fact, the model free ID. The model free ID is the following. The model free ID is the following: is that the only information that you have about the channel is the sampled response of the channel on the pilot. That's the only information that you have. In this particular example, I used pilot, which are just the same standard pulson. Okay. But you can apply the same ID for spread pilot. So I gave you the very simple example of pilot region and data region, just to avoid complexity, to avoid abstracting the discussion even further. The whole idea of model free is that you take the sampled response of the pilot and you don't add any additional prior knowledge to it, and you use it. In this particular example, I used a pilot region, standard pulson for pilot, devoted full strip. It's wasteful implementation, of course, and I used it to sense the channel. Yes.
I see.
Am I clear?
I think so. Thank you very much. Okay. Yeah. Now let's jump outside of the channel part.
I see a very nice question of Rawan. Is there anything that can be done to reduce the out of spectrum band emission of OTFS? Wonderful question. Thank you, Rawan. Look, in fact, there is a fourth paper coming soon with Saif, Prof, and Rob, exactly about this question. But I want to give you the answer. The answer is very simple. Because I heard in many discussions, people advocating filter bank OTFS, just to take care of this out of band emission is worrisome to many people, and for good reason. OTFS. Let's talk about Zak OTFS. In Zak OTFS, what shapes the bandwidth, and the duration is the delay-Doppler filter. Okay, you have this delay-Doppler filter, which is shaping the pulse in delay-Doppler. The pulse have a certain structure. What is shaping the structure of the pulse in delay-Doppler is a function on the delay-Doppler called the delay-Doppler filter. This function will dictate the effective band, will dictate the effective duration, and will also dictate the energy envelope of these things. Yes. If you use sinc function to shape your pulse, you will get a lot of out of band emission. If you use raised cosine for this shaping filter, you will get much less out of band emission. And in fact, in this recent paper that will appear soon, the point that I'm trying to make, you can choose any function that you want. It's an unconstrained problem. You can choose functions for this delay-Doppler filter that will have very small out-of-band emission. So within the framework of Zak OTFS, you can have complete control over the out-of-band emission. You don't need to go to filter banks. You don't need to go to all these things which are not really relevant to OTFS. It's a design problem of your delay-Doppler filter. And you can make the out-of-band emission to be very, very small. Yes.
I also have a follow-up question on this. Yeah. Like when you are talking about using different filters in the delay-Doppler domain to control the spectrum and the mask, will that affect the orthogonality in delay-Doppler domain?
Great point, Lee. Also, I like this point. OTFS is not an orthogonal modulation. I apologize to the community that we call it orthogonal time frequency space. It's an historical error. I always apologize for that. OTFS is the opposite of an orthogonal modulation. OTFS embraces intersymbol interference.
Yes.
So you see, orthogonality in general is a very sensitive phenomena. It only happens when the channel is trivial. So when you have a little bit of channel, OTFS is already not orthogonal. Now, just give up of orthogonality altogether. You can use filters which are not orthogonal also in line of sight channel. Doesn't matter. Who cares? OTFS is not an orthogonal modulation. In OTFS, you acquire the intersymbol interference as part of your input-output relation, and you equalize them. And I don't care. I can use filters where the orthogonality breaks down already for trivial channels, and I will equalize it, and it's perfectly fine. So orthogonality is not important.
I see. Isn't that in the sense that the pulse is sufficiently narrow, therefore there's orthogonal or not?
Typically, why people use sync pulse or raised cosine? They use sync pulse and raised cosine because they vanish on the grid point. They vanish on the grid points of the information grid, which imply that if the channel is trivial, if the channel is identity, then you can actually read the data without equalization.
That's right. Yes.
But this is a kind of irrelevant. This is a very sensitive phenomenon. If the channel is already very small, it will create in OTFS intersymbol interference, and you need to equalize. So just give up of the orthogonality altogether. Just forget about this property of vanishing on the grid point. Take whatever function you want and equalize the intersymbol interference, and that's it.
Okay, thank you for the answer. And I saw that Professor Farhan is asking about the USM technology from Cohere company. Do you have any comments on that in comparison to the
comment? So Cohere is a company. I have the word Cohere on the. I represent now the University of Texas 50% in Cohere. I always represent Cohere also. But Cohere started with OTFS, trying to push it to 5G, and of course, eventually it was not successful. It will try to push OTFS again for 6G. But what Cohere did, it had to eventually pivot its business plan to take derivatives of the delay-Doppler technology that can be implemented within existing standards. So the UFM technology of Cohere, for people who are interested, is a precoding technique. It's a beamforming technique, which is using the delay-Doppler representation of the channel. So I told you about the channel that the characteristic attributes of the channel are the delay, the Doppler, and the propagation loss. So Cohere technology, the product that Cohere is proposing to the industry is a beamforming technique, which is based on these stable parameters, and this can operate in FDD and in TDD. So it's just taking the delay Doppler channel representation seriously and trying to do standard technology using this representation.
Okay, thank you.
That's the USM, by the way. So the USM is a beamforming technique which can operate almost always, and in particular, it allows coexistence of OTFS and OFDM. So that's maybe the importance of that to the future of OTFS, future standard.
Okay. Still questions. Do you think CPs are important for OTFS? Reduce CP, like CP, what different type
I think that, again, that in OTFS, CP is more like guardband within the delay. That's my understanding. Again, we are all of us that gain experience with delay Doppler signal processing, we are building our own, mental picture of what. For me, CP is just a type of guardband that you incorporate within the delay Doppler domain in order to simplify some signal processing. They don't play any fundamental role. So I think the healthy perspective about OTFS is that there is no CP. If you want to include a certain guardband, always stay with the paradigm of Zak. So don't include all kinds of artificial things in the time domain. Don't do that. It's not healthy mathematically to do that. Just if you need to include certain guardbands in the delay Doppler domain in order to facilitate easier equalizations or things like that, I'm fine with that. But it doesn't play any fundamental role like in OFDM. In OFDM, CP plays a fundamental role to create the input-output relation. So in OFDM, if you don't include CP, you will get an input-output relation that you cannot acquire and you cannot equalize in principle. So you must put the CP in order to be able to operate. In OTFS, no. OTFS CP is just a luxury. You can put it if you want to. CP may be guardband, the input-output relation it does not require a CP.
I see. Okay, thank you. What about frame synchronization?
Frame synchronization, that's an issue that exists in any. I would propose for frame synchronization. This is a research topic for people who are interested. I think people did work about that, but for frame synchronization, to the best of my knowledge, people are using traditionally Zadov-Chu and all these kind of use pulsons. You need frame synchronization, so maybe you can do it using the pilot. Remember, you have a pilot within the you have a sensing and a communication. I like to think about joint sensing and communication as two things which already in OTFS sensing and communication by definition happen together, because in OTFS the channel acquisition is a radar problem. So just use the pilot, use the sensing pilot for synchronization. So you're using pulson for synchronization, and this can have benefits because pulson, if you know a little bit about Zadov-Chu, they are sensitive to Doppler. They are good for delay, synchronizing in delay, but when you have presence of Doppler, Zadov-Chu breaks down. You get ambiguity. Because the ambiguity function of a Zadov-Chu is a line, it's a chirp, it's a line in the time frequency plane. While the ambiguity function of a pulson is a lattice. Basically, it's a thumbnail. It's just a zero and some and so you can so pulsons in fact give you a synchronizing mechanism which is stable to Doppler. And you can use the pilot for that. You don't need additional yes.
Okay. There's another.
I see an interesting paper, interesting question from Kai. If there is no CP required, how does OTFS prevent interference from different OTFS frames? Good question. So you need a guard band on the level of the OTFS packet to separate between frames. But it's not that you need a CP on every, it's a very small proportion. Think about it. An OTFS frame consists of 10,000 symbols. It's a huge. So on the level of the frame, you do need some mechanism to intercept interframe interference. But it's not the same mechanism that you use within the frame. Within the frame, you don't need CP.
True. Okay. Another question about resource allocation. Right?
Yes.
So in conventional OFDM cases, resource allocation is quite different from what we have in the delay-Doppler domain. What do you think of the resource allocation design in delay-Doppler?
Very good question. Again, research. You can go in various directions. You can use guard bands. That's the most. You can allocate. You can split. And you can do superimpose. You can give every user a different rotated pulson and start to consider resource allocation in a CDMA-like manner. But now it's not that one code for a user, but you can give one pulson for a user which he can transmit a full frame with it. So you can do this superimposed thing. So there are so many degrees of freedom. I don't consider myself an expert, but I can see different things. You can and again you can also use what is resource allocation. So I can give you another interpretation. So in OFDM, resource allocation is just giving orthogonal subframes, orthogonal sub pieces of the bandwidth to different users. So the OTFS analog of that is that you are using the delay-Doppler filter. You are giving every user a delay-Doppler filter, which allocate for this user a piece of the band and a piece of the time. You see, the delay-Doppler filter tells you which piece of band and which piece of time is allocated for the frame. So you can do orthogonal allocation using filters. Every user is given a filter which allocates for it a different time frequency box. And in this way, you create orthogonal allocation in OTFS. So you can go through, you can do orthogonal allocation using these orthogonal filters. You can do superimposed allocation using the CDMA, using unbiased pulsons. You can do guard band allocation by partitioning the delay-Doppler to different users. So there are many options.
I see. Okay. There are some questions that I personally interested very much. It's about the Heisenberg uncertainty principle. As you have mentioned, in delay-Doppler, there is a way to get away of this constraint. But if I recall correctly, the Heisenberg uncertainty principle is defined for a dual Fourier functions, but delay and Doppler, they are not duals. Is that the reason why there is no constraint?
So let me give you interpretation.
Mm-hmm.
The Heisenberg uncertainty principle has many disguises. It's a monster with many heads, and all the heads are connected to the same body. One of the ways to interpret the Heisenberg uncertainty allocation is that when you look at the ambiguity function of a signal, I like this way because it's independent of the signal space that you are using. I don't care whether it's delay-Doppler. When you look at the ambiguity function of your signal, it is constrained to have a certain volume. For example, in the naive interpretation of the Heisenberg is that when you look at the ambiguity function of your signal, it is located at 0, and it has a characteristic width, which is 1.
Yes.
So in the optimal construction under this interpretation is the Gaussian. The Gaussian is the one which optimizes the Heisenberg uncertainty principle when the ambiguity function is only located at 0. Okay? But so the question that you can ask is how the pulson what is the dialogue between the pulson and this picture of the Heisenberg uncertainty principle? Okay? So what the pulson is doing, which the Gaussian is not doing, or how the pulson is cheating the Heisenberg uncertainty principle from this perspective. So what the pulson, if you look at the ambiguity function of the pulson, you are going to see it's very, very different than the one of the Gaussian. The ambiguity of the function of the pulson, it's going to have the following structure. It's going to be a very, very narrow pulse at 0. Very, very narrow. The dimension of this, the characteristic volume of this pulse or area of this pulse is going to be the bandwidth time, 1 over the bandwidth time the duration. It's tiny pulse, it's not 1. But then this pulse repeats on every one of the period grid points.
Yes.
That's the price that you pay so not to violate the Heisenberg uncertainty principle. So it's a very, very narrow pulse, which is repeating itself on a lattice of area 1. So, and there is a signal which has this ambiguity function, it's the pulson. And the point is that this signal is to every practical, for every practical purpose, behave like a single pulse in 0, because if the spreads are smaller than the period, who cares about these aliases which appear on the other grid points? You are basically dealing with a pulse, a single pulse. So, so that's I think the reconciliation between the traditional idea about the Heisenberg uncertainty principle and the pulson.
I see.
Yeah.
Thank you very much. I think there is the final question that you have mentioned that OTFS, the advantage or Zak OTFS is that there is no overlapping and no selectivity, right?
No selectivity in this sense that I explained, yeah.
Yes. Do you think OTFS or Zak transform OTFS is the only waveform that can achieve this? Because I realized recently there are many waveforms that claim very similar opinions. And what's your opinion on these different novel waveforms, for example?
I think it's the only. But you know, I'm religious.
I see.
So
I see.
I think it's the only waveform. I think if you scrutinize, put a level of scrutiny, the other waveform. For example, there is this chirp, this affine modulation, which is using chirp.
Yeah, I also saw that. Yeah.
This modulation cannot. You see, chirps and tones are the same. Mathematically speaking, chirps and tones are the same. If you look at the ambiguity function of a chirp, if you look at the ambiguity function of a tone, it's a line. It's a line. It's the horizontal line. So you have ambiguity along delay. If you look at the ambiguity function of a pulse in time, of a delta function in time, it's a vertical line. If you look at the ambiguity function of a chirp, it's a diagonal line.
Yes.
So the ambiguity function is still a line. So chirps, deltas, and tones belong to the same family, and now no one will win over the other. The ambiguity function of a pulson is a lattice. Very, very different. And because of that, because when the lattice is bigger than the spread, the pulson, this is very stable geometric argument. This crystallization phenomena come from the fact that the support of the ambiguity function and the spread of the channels are, in a sense, they have a certain geometric relation to one another. And only the lattices, from all the way from the tie node, only the lattices will have this geometric relation to spread that will make them crystalline. All the other examples do not make sense to me in this sense. Or maybe they are interesting waveforms, but here there is a very, very fundamental way to think about the thing. So my religious answer is that no, I think that the crystalline regime is the only way to achieve this particular attribute in the way I expressed it. But again, it's not a fair question to ask, because to prove that you don't have a sister, how do you prove that something does not exist?
I see. Thank you for the answers. That's very interesting opinion from you. Yes. Okay, I think we pretty much covered all the questions in this talk, and thank you again for the excellent presentation. And please, if the book is out, please let me know, and I can broadcast to all the audience. And I'm very looking forward to this book.
My pleasure, my pleasure. Thank you very much for inviting me, and I hope the audience enjoyed the talk and was able to learn something.
Okay, thank you very much, and thank you for your time. See you guys next time. Bye-bye.